Hello and welcome to this presentation of Natural Resources Canada's Air Source Heat Pump Sizing and Selection Toolkit. This toolkit's a free resource available on the NRCan website. The toolkit includes a package of materials related to electric air source heat pump sizing and selection, intended for use by mechanical system designers and renovation contractors. The materials were designed to assist these individuals with sizing and selecting electric air-to-air heat pumps for Canadian climates in both new and existing or retrofit residential applications. In today's video, we'll cover the two main elements of the toolkit. So first, we'll examine the sizing selection guide, which outlines the key concepts and principles for air source heat pump sizing and selection. Then we'll see how the companion tool can support the application of these principles through two worked examples involving both ducted and ductless systems. As a reminder, the guide and tool are really designed to support you in your design process. However, final sizing and selection of an air source heat pump for a specific project remains the responsibility of the mechanical contractor or designer. With that, we can begin our discussion by looking at the key concepts outlined in the air source heat pump sizing and selection guide.
I'll go through the heat pump sizing and selection toolkit, as we call it, which includes the guide, a worksheet that goes with the guide, an addendum of worked examples, and the tool. So I'll jump right into it. So I'm going to go through the guide and basically the paper side of things, the paper documents and the procedure that's in the guide. And then I'll hand it over to Justin for going through the tool examples. So first, just a couple slides on why this matters. Basically undersizing, as we know, can lead to insufficient cooling or heating. So that's definitely not a good thing. We always avoid that when we're sizing systems to heat and cool people's homes. But oversizing, which is less obvious, can result in poor performance due to cycling or comfort swings. And we see that with systems, and that's particularly the case with air source heat pumps when they're oversized. They may be variable capacity, and they may be able to ramp down. But any system, if it's oversized, will start to cycle. And heat pumps don't like to cycle; they like to run on long run times. So we really want to focus on sizing and selecting the right system for the application for those reasons. And we know that these can lead to poor performance, ultimately unhappy homeowners, callbacks to the contractor potentially, and unhappy builders. And in the past, in the late 90s and early 2000s, we didn't have cold climate air source heat pumps. Air source heat pumps tended to have a cutout around -5 or drop off in capacity quite substantially at that temperature. And so there's sort of a bad reputation for air source heat pumps that's been out there historically, and I think that's changing now over time. And much like furnaces have gone from a single stage furnace to now fully modulating furnaces, we have the same situation with air source heat pumps, and we have heat pumps that can perform very well down to cold temperatures that can cover the majority of our heating loads in many locations in Canada. So that's what's happening in the industry. We also know that there's a trend towards right sizing. We know with the F28012, we got closer to a heat loss and heat gain calculation that actually is what we observe in the field. And so we can size equipment with confidence closer to the load and not oversize like we used to have to do. And there's a trend towards doing that both on the equipment marketing side and on the design side. And just a little bit about sizing until now. In the previous HRAI residential air systems design course, which many people may have taken, and they would have been taught that heat pumps sized for heating and cooling applications, which would be most of the applications in Canada, would need to be sized to the nominal cooling capacity, and they would be correctly sized if they were sized at between 80 and 125% of the design heat gain. And that's fine for systems that are, designed for covering cooling loads, and that will get you some part of the heating load, but it won't get you as much of the heating load as you could if you were to upsize the heat pump a bit. And so the only way you could do that previously, if you were taught through RESD, was to size for heating only applications. And there you were taught to size between the heat loss at 35 Fahrenheit, which is a little bit above zero, and then the heat loss at 17 Fahrenheit, which is -8 Celsius. And that gets you sort of a medium-sized heat pump, which is good, gets us closer to what we're hoping to do with heat pumps covering more of the heating load, but doesn't give us, the options that we think we could have given the capabilities of today's heat pumps. So I'll get back to where HRAI is now in their RASD, but I just wanted to give you a bit of background. So in terms of the sizing and selection guide and toolkit, it is aligned with the revised HRAI RASD, and it complements guidance offered by TECA out in BC, the Home Performance Stakeholders Council in BC, as well as NIA and NEEP. We worked through the NEEP guides when we were developing this guide, so we learned from some of those experiences. It provides selection guidance that's specific to retrofit and new applications. It covers centrally ducted, ductless mini splits, multi-splits, as well as compact or mini ducted systems. It's specific to single stage, two stage, and multi-stage or variable capacity equipment. And it really is intended as a learning tool. And it's specific for sizing and selecting air source heat pumps. And the target audience is HVAC trades, designers, and contractors. As Lorene said, it could be used to estimate heat pump sizing for the Greener Homes program, but a qualified person who's sizing and selection equipment should be the ultimate person to make that selection and size decision. It's not a project feasibility tool like RetScreen, if you're familiar with that tool, also offered by NRCan. It's not a simulation tool like Hot 2000 or Energy Plus. And it's not a heat loss, heat gain, or duct sizing tool like is offered by Quality First or RightSoft. And just to give you sort of, I guess, get you thinking about some examples where you might have encountered in the field where this guide is going to help you. I'll run through just a few scenarios, get you thinking about things, and then I'll go through the procedure that the guide follows, and then I'll hand it off to Justin. So here's a few common examples that we've come across through the 3 years that we went through in developing the guide. I'm installing a hybrid system, for example, or a dual fuel system that combines a gas furnace with an air source heat pump. Is a cold climate heat pump appropriate for this application, or does a two-stage or single-stage heat pump perhaps make sense, given that I've got that gas furnace kicking on at the coldest times of the year? Or my client has a condensing gas furnace with an EC fan motor. Maybe they've gone through an EnerGuide program in the past and had their furnace replaced with a high-efficiency furnace with EC fan motor, but maybe they didn't replace their AC, so maybe they need a new AC. Is there an upsell opportunity to offer a heat pump instead of a standard AC? How do I select the right heat pump if I'm doing that? And does the thermostat that the homeowner currently has support the heat pump that I'm looking into? Or if you're in Ontario and you live in a region with time of use rates for electricity, what would be the appropriate switchover temperature from the heat pump to furnace if it's a hybrid or dual fuel system installation? Can you use an economic switchover temperature where the system switches to gas or to electricity for the heat pump based on least cost? Or, maybe you're in Atlantic Canada or out in BC, or also go back to Ontario, where you're looking for mini splits to displace some of the heating and provide cooling in an electric baseboarded heated home. Which mini split would be right for the zone load? How do you size and select the mini split for just that specific zone load? Or do you go with a multi-split system? My client's looking for a cold climate air source heat pump to cover the whole heating load in a high performance or net zero energy home, should I size at the design load, or should I size for a little less and cover the coldest conditions with electric backup? What might happen in this scenario in cooling? If I do size for the whole load, will the system be capable of ramping down in cooling to not be oversized and short cycling during cooling? So all these scenarios we try to address through the procedure that's followed in the guide. So again, the guide, as we're calling it, a toolkit. It's offered in 4 components. There's the guide itself, which is about a 60, 70-page document that if it's your first time sizing and selecting an air source heat pump is a useful thing to go through. It walks you through each of the procedural steps and provides some links to resources to get data on for heat pump performance, for example, and just steps you through all the calculations that are made that are actually automated in the tool. There's a 1-page summary worksheet, and that's intended as something you could take on a clipboard to a job site. You could make note of the installation application, like whether it's a mini split, whether it's centrally ducted, how many heads you're going to get installed. You could take note of your design heating and cooling loads, and then walk you through sort of the rest of the decisions and for note taking as you go. There's also this sizing and selection tool, which is an Excel-based tool that follows the same procedure as the guide and just automates some of the calculations that are done by hand in the guide and provides some additional charting functionalities as well as sort of high-level cost, GHG, and energy saving analysis to help you with the decision. And then there's an addendum of work examples, and that's really aimed at stepping you through a specific case study through each of the steps in the procedure. And it's very useful if you've got a job in mind and you want to just see how the guide could be used to help you out with that. You could find the appropriate example in that addendum and read through it, and I think that would help you really understand what's in the guide. So now I'll just go through the 7 steps to give you an idea of what we're doing in it, and I think that'll help you with sort of some overall knowledge of where we're going with it before jumping into the tool. So in step 1, you define the air source heat pump configuration, and that's really, is it a new system? Is it an add-on to an existing system? Is it centrally ducted or is it ductless? And if it's ductless, then step 2 would be you would choose the mini split indoor unit types. We have floor mounted, ceiling mounted, wall mounted, and mini ducted systems. So there's lots of different options. These first 2 steps don't really affect sizing and selection choice, or your sizing choice rather. They affect your selection, but they're really intended to help you follow through the decision logic. Step 3 is where you're going to be defining what you're sizing to. So you're determining the design heating and cooling loads. You would be doing that external to the guide and to the tool via HOT 2000 or an F28012 full calculation, or perhaps you've already had an energy audit done, then you would be able to extract the data from that report. So you define what those loads are. And in step 4, you're going to be determining the sizing approach to meeting those loads. And there's 4 approaches that are described in the guide that are kind of shown on the right hand there, little graphic. There's 2 approaches that are sizing to the cooling load, and there's 2 approaches that are sizing to the heating load. One is sizing to the heating load at 17 Fahrenheit or -8, and the other is sizing to the full heating load. So once you determine which approach you're going to go with, and that would be determined via, the client's needs, basically. If the client's interested in sizing to cooling, or if they want a system that accomplishes more of the heating or all of the heating, then that would help you to determine which approach you're using. Once you do that, then you've got your air source heat pump target capacity requirement. So that's what your capacity is at an outdoor temperature that you're going to use to then select your air source heat pump. And at step 5, that's what you're doing. You're identifying the candidate air source heat pumps that are going to match those key requirements. And you might work through product that you're familiar with. You might explore new products, and then basically match the capacity of those systems to the loads, and based on which sizing approach you're using is going to determine the temperature that you're targeting at. So from there, you make your final air source heat pump choice. You know, which system is best for the load and application conditions. And the tool will provide you some knowledge to help you make that decision. Once you've decided on that, you've chosen on the air source heat pumps you want to select, then you would define what the system control strategy is. So, you know, how is the air source heat pump switching to backup, if there is backup? Is it doing it based on a thermal balance point, which is sort of the typical setup? Is it doing it based on an economic balance point? So switching based on least cost of fuels, if it's dual fuel, for example? Or is it doing it based on a cutoff temperature where the system is controlled to operate to a certain outdoor temperature, and then it just switches to backup at that temperature, so there's a lockout. And in step 7 is the last step. You would define the backup heating requirements, if there is backup heating requirements needed, or if a backup heating system isn't already in place. So that's really the 7-step procedure. And I wanted to just give you a sense of what's in the Addendum of Work examples. As I said, there's a centrally ducted and a ductless example for each sizing option. So sizing option A is you size for cooling. And then we've got a full system replacement example with a centrally ducted system, or an air source heat pump add-on example with a ductless system. And option B is where you size for balanced heating and cooling. And there again, we've got a ducted and a ductless example. Option C is where you're sizing at 17 Fahrenheit. You've got an emphasis on heating. 2 examples there. And option D is your sizing for the full design heating load. And there we had 2 examples as well. And our second example on that one is a multi-zone ductless add-on. And I should note that each of these examples uses a 2-head system, which is aligned with the Greener Homes program targeting a minimum of 2-head systems. So I think you'll find these helpful. And I just made a note of a few examples that when Justin presents on the tool, he'll cover basically a B2, C1, and C2 sizing example. Now, just making full circle the HRAI residential air systems design coursework that's now been modified, and you've got a few options now for sizing your heat pump when taught in that class, and they align directly with the air source heat pump sizing and selection guide. We were in constant discussion with HRAI throughout this process, which is great to be aligned. So their first option is a heat pump is to be used primarily for cooling and not so much for heating. That's option 4A and B in our guide. Heat pump is to be used as a primary heating source. That's option 4C in the guide. And the heat pump is to be used as only source of heating and cooling without supplementary heat. That's aligned with option 4D in the guide. So if you want to find everything, I put the the link in the chat there. Here it is. If you just Google search, NRCan air source heat pump sizing and selection, you'll find it, and you'll get the links to the various components. And I'll hand it over to Justin now to go through the tool. Thank you for your attention.
So in the second half of today's presentation, we're going to look a little bit more at the air source heat pump sizing tool. So Jeremy really took you in some of the previous discussing some of the principles about heat pump sizing and why it's really important. In this section of the presentation, I'm really going to show how the air source heat pump sizing tool that we've developed can really support you in the application of those principles. And the way that we're going to do it is we're going to do two different worked examples. One that's a centrally ducted system and one that's a single mini split system. And as I go through each of the examples, I'm going to showcase some of the functionality of the tool. And I'll also try as much as possible to just provide some guidance and some quick sort of tips and thoughts about heat pump sizing and selection as we go. So the first system that we're going to look at is a centrally ducted example. So for this particular worked example, let's assume that we have an existing single family home, say it's located in Toronto, and the current system is a ducted natural gas furnace. We've done a nice F28012 load analysis, so we have a good understanding of what our heating and cooling loads are at our design temperatures already, and we can help to feed that into the design process. So the homeowners come to us and they've told us they have a couple of goals. Number one, they want a completely new heating system. So they want to take the furnace out, replace it with a new heating system, but they want to keep the ducting as is. They're also looking to cover a good portion of the annual heating demands of the building with the heat pump, but perhaps they're not necessarily sure whether they're going to cover the 100% of the full loads of the building. In addition, they might have another question for you. Is it better that they have sort of a hybrid natural gas and air source heat pump system, or should they just have sort of a singular air source heat pump with an electric backup to supplement heat pump operations when required? So with that, we might have a couple of different sizing questions already in mind. Maybe we have a certain model range that we're used to working with, but we're not sure what size of unit's going to be best. Perhaps we're not sure how to set up the controls of that unit. So if you have both a heat pump and a natural gas furnace, when should you transition between those two systems, for example? As well, when we're talking with the homeowner, we might be interested in letting them know how much of the load the heat pump is estimated to be able to cover, sort of in terms of the annual heating requirements of that building. So with that context in mind, I'm going to do now a worked example using the air source heat pump sizing tool. So what you can see on my screen right now is basically the sort of newest version that's going to be coming up on the website in, I believe, about 2 or 3 weeks. And basically what the tool is it's an Excel-based electronic representation of the guide that Jeremy already went through. And the way that it's organized is that each tab corresponds to a specific step in the guide. And so in doing so, it's really designed to help to support some of your design decisions, but also sort of carefully scope out each step and sort of step you through the process of sizing and selecting a heat pump. So right now I'm on sort of the introduction page. So from a user perspective, the most important thing that you're going to want to note here is that there's a little drop-down menu that allows you to select between imperial and or metric units. Now, in my case, I'm more used to working with heat pump capacities and sort of system sizing in terms of BTU per hour. So I'm going to generally go with imperial for my particular selection today. Moving on, we'll have an additional sort of licensing agreement, which is just your standard end user license agreement. And then we have step one, which is really sort of sketching the initial sort of outline of your system. So the first thing that you're going to want to be able to enter, or that the guide and the tool is going to ask you, is what sort of air source heat pump configuration are we going to be looking at? So we have 4 different options here. We have essentially ducted air source heat pump, And then we have three different sort of variations on mini split systems, whether those are ducted mini split systems or whether they're ductless, single, or multi-zone systems. Now, as I mentioned, in this particular example, we're interested in essentially ducted air source heat pump. So I'm going to select option A. The next thing that the tool is going to ask you is, what sort of installation type are we going to be looking at? And when I click the drop-down menu here, we're going to be able to see three different options. And so I'm just going to zoom in a little bit here, just so that it's a little bit more clear. And basically, you're going to have three different options. The first is a new HVAC system. So this is really where everything is new. You have new ducting and a new heating system as well. In addition, the next option is what we would call a full system replacement. So here, we're keeping the existing ductwork of the home, but we're completely replacing the heating and cooling equipment. So this would be a situation where, for example, we're replacing the furnace with a heat pump in an existing home. The last option that you have available to you is what we would call sort of an add-on heat pump. So here, you might be keeping the existing sort of base heating system to use as a backup, and you're just installing the heat pump as an add-on. So a nice example here, and we'll see it in one of the worked examples later, is a situation where maybe you have a home that's heated using electric baseboards, and you're looking to integrate a heat pump into that. So in that situation, you probably keep your baseboards as a backup and install a heat pump to try to take care of most of the heating demands of your building. In this particular example, as I mentioned, the homeowner wants to keep the existing ductwork, but they want to replace the existing heating system. So in this particular case, I'm going to select the full system replacement as my selection. So with that, I can then move on to step 2. And if I click on step 2 here, I can see that I don't have any selections or anything to do. And that's because on step 1, I selected a centrally ducted system. Had I not, and had I selected a mini split system, I would have additional options here to really specify the different types of indoor units that I'm going to be using. And we'll see some of those options a little bit more in the second worked example. Now, step 3 is a step that is really looking to provide a little bit more information about the specific project of interest. And it's an extremely important step in the general process of sizing and selecting your air source heat pump. So the first thing that we're going to be doing is just defining where our particular project is. And we're going to have, in the tool right now, we have locations both for Canada and the US, and a fairly complete set of cities and states and provinces comprising that. In terms of Canada, we have all of the provinces and territories built into the tool, along with a fairly good selection of cities in each of those provinces or territories as well. For today, our case study is going to be in Toronto, so I'm just going to select Ontario. And then I'll just show you here that in terms of Ontario, as you can see, we do have a quite substantial selection of cities as well. So when you finally select the location, what the tool is going to do is it's going to pre-populate a couple different things for you. First off, it's going to identify the particular climate zone that your city is going to be located in. It's going to pre-populate the heating degree days associated with that location. And it's also going to already specify for you the design temperatures both in heating and in cooling. So you're not going to have to go back to the building code or other sets of documents and try to dig that information up. The next thing that the tool is going to ask you, and it's a fairly important step, is what was your method of determining the loads? So as Jeremy mentioned a little bit earlier on in the presentation, one of the things that the tool does not do for you is it will not calculate the loads of the building for you. We really rely on the users to do that calculation, ideally through a CSA F28012 compliant method. If I click on the drop-down menu here, it's going to provide me with basically 4 different options that are sort of potential for deriving those loads. Number 1, obviously, is that CSA F28012 load analysis, which is, I think, really the way that we encourage everyone to go. In addition, perhaps you have a HOT 2000 simulation that's providing you the heating and cooling loads of the building as well. It's another option potentially for specifying what those loads are in the tool. We also have what we call option B, which is a post-retrofit load estimate. And so if you have an energy audit that was done perhaps in the past for the building, sometimes these reports contain information that'll say, they'll give you the design loads, but they'll also give you sort of the percentage of savings possible by performing all of the all recommended non-space heating upgrades. And so what you can do using that percentage savings possible and the loads that are specified in the report that would essentially be possible if all the building envelope retrofits were implemented, the tool can sort of back calculate for you what your actual design loads would be. And then it specifies it here under step 3, design outputs. The last option that we have is estimating loads from existing equipment. This is something that we really sort of discourage you from using if possible. The best option is always to try to do appropriate load calculations and load analysis on your buildings. However, if really that was the only way that you were able to go, you'd be able to sort of enter what the rated heating and cooling equipment capacities were, and then sort of back calculate what the estimated loads might be by assuming a certain oversizing factor. If I have to stress one thing about this particular tab though, it's that load calculation and appropriate load calculation is extremely important. If you have a load calculation that's already oversized versus sort of the true load of the building, that's likely going to lead to oversized heat pumps, which in turn can lead to issues like cycling and thermal comfort issues, which at the end of the day can result in more callbacks. And those are things that I think ideally everyone would like to avoid. In this particular example though, we're going to assume that we have that F28012 load analysis done, so I've selected option A. Now the last thing as I scroll down on this particular tab that I'm going to see is that because I selected sort of what we call the full system replacement, I have these additional inputs here where I'm able to sort of enter a little bit of information on the existing ductwork in my particular building. So that ductwork, I can say it's rectangular, it's round, maybe it's a combination of both. I can specify the number of trunks that I have, and then I can also specify just here on the right some of the dimensions that are associated with the ductwork. And so what the tool does is it takes that information that you enter and it does a calculation to sort of determine what the airflow capacity of your ductwork is based on sort of a maximum trunk velocity of around 900 feet per minute. which is derived from the HRAI Residential Air Systems Design course. And so what the tool will do later on is that it'll compare this airflow capacity with the estimated airflow of the heat pump that you enter, and it'll flag for you whether the heat pump that you're looking at potentially has a higher flow rate versus what the airflow capacity of the ductwork was calculated. And it'll just sort of suggest that you might want to think about that, or just do a double check to make sure that's the design path that you want to use going forward. So next, I'm going to move on to step 4. And in step 4, it's really about sort of identifying the method that we want to use to size our heat pump. So when I click on the drop-down menu for sizing approach, I'm going to have another 4 options available to me. So option A and option B are sort of evolutions on, I think, what has been the design practice in the past, which has been primarily sort of focusing on the cooling loads of the building. And I'll get into a little bit more detail in the ductless mini split example, explaining the variation between option A and option B. When we're looking at sizing more for the heating loads of the building, option C and option D are really the options that are probably of most interest for us. So in option C, it's really about selecting a heat pump so that the heat pump capacity matches the building load at 17 degrees F. So when I select option C, the tool will sort of pre-populate out for me what that target heating capacity is. And then if I just scroll down here, it's going to plot out the load line for me based on my design loads and temperatures. And it's also going to identify what my target air source heat pump capacity is. Now, the other option that's available is option D, which is really sizing the air source heat pump to cover the full heating loads of your building at the design temperature. And so your selection between option C and option D is really going to be dependent on a couple of things. First of all, your sort of the goals of your client, but as well the climate that you're looking to implement this heat pump system in. So there's certain regions in Canada that you're going to have design temperatures below minus 25, minus 30. And in those situations, you're really going to struggle to find an air source heat pump that's going to be able to meet the full heating loads of the building at those temperatures, or even really operate below minus 30. So those are some of the things to keep in mind when we're sort of evaluating between option C and option D. Now, in this particular case, I said that our homeowner was interested in covering a good portion of heating, but not 100%. So in this case, I'm going to use option C as my sort of initial sizing approach. The next step is step number 5. And step number 5 is really where you're probably going to be spending most of your time. And it's really a step where we're really evaluating some of the different heat pump options that we have and examining how they respond to the design goals that we've set forth. So the first thing that the tool is going to ask you is how many heat pumps do we want to look at? And you can select between 1 all the way up into 4. For this initial analysis, I'm going to set it at 2 just to show you some things, and then I'll move it back to 4 to show you how we can sort of compare a number of the options that are available. As I scroll down into this heat pump input section, this is really where we start adding a little bit more information about the heat pumps that we're interested in. So first of all, we just enter some general tracking information about the model name that we're interested in, the noise rating as well. And as well the rated airflow of the system. And as I mentioned, that rated airflow is then compared with the airflow capacity of the ductwork, just to try to identify whether there might be any potential problems. Next off, as I scroll down, you'll have an option to be able to indicate what type of heat pump you're going to be looking at. Is it a variable capacity system? Is it a two-stage system, a single-stage system? And in the current version right now, which particular stage of the system we're sort of entering information for, whether that's the high stage or the low stage. Now, as a minimum, in terms of the data inputs for capacity and either power or COP, we require the user to enter the information at 47 degrees F, 17 degrees F, and 95 degrees F in cooling. You will have the option of entering information in terms of heat pump power, if that's easier for you, or the heat pump COP as well. Now, the tool, I think, like sort of any other sort of computer program, the more information that you provide to it, the better a job it's going to be able to do in terms of performing its calculations and supporting some of the design decisions that you're looking to derive from this particular tool. So we also offer the user the ability to enter additional data points. So if I scroll down here, I can see sort of a table that I've already pre-populated out, where I've sort of indicated that I have additional information that, in my case, I was able to derive from a manufacturer-supplied manual in which they had data tables for the heating and cooling capacities at various outdoor temperatures. So basically, I indicated how many data points I had above 47, between 47 and 17, below 17 as well, and a similar idea in cooling. And then I just filled out what the heating capacity, and in my case, what the heating power was at those locations or at those particular temperature points. Now, one thing that is a little bit of a limitation of the tool right now, but it's something that we're really working on hard at the moment to fix for a version that will come out at the end of August, is sort of when you're entering information for variable capacity systems. So right now, what we recommend that you do, if you do have a variable capacity or a two-stage system, is that you enter the high stage as one heat pump. So in this particular example, heat pump 1, I've entered it as the high stage. And then for heat pump 2, I've entered that as the low stage for that same unit. And that just allows me to plot out both of those capacity curves, as we'll see a little bit later, and helps me to derive a little bit more information from it. In future iterations of the tool, you won't have that issue, and you'll be able to specify both the high and the low stage as a single sort of heat pump entry. Now, I'm sure a lot of you right now are probably thinking, that's this is an okay way of entering the heat pump data, but is there any way that we could link to some form of database to sort of pre-populate out a lot of this information? So that's something that I know Jeremy and I have discussed a lot, and I think it's something that we'll try to look at a little bit more in detail in the medium to longer term with this particular tool. But right now, I think that we'll sort of rely on sort of deriving the information from available manufacturer specifications, AHRI cut sheets, and things of that nature, and entering the information into the tool. But eventually, I think, again, we'll try to evaluate the option of potentially linking to other databases that might be available. So as I scroll down here, one of the nice things about the tool is that it provides you with a number of sort of graphical interpretations of the data that you provided. So what I can see in this particular sort of graph here is that I have the load line that was sort of plotted out initially in step number 4, but now I have my heat pump capacity curves overlaid on top of that information. So I can really understand how that system selection sort of compares to my design goals. So as I mentioned just a little bit earlier, I entered basically the high stage of the variable capacity heat pump as what would be referred to as heat pump 1, and the low stage as heat pump number 2. And so from this graph, I can already see a couple things that are pretty important to note. So first off here, I can see this little dashed line, which is indicating what my thermal balance point temperature is for the high stage system. So basically what that means is that below that balance point temperature, the heat pump is not going to be able to meet the full heating loads of the building on its own, and it's going to require some form of supplementary heating. Above that balance point temperature, the heat pump is going to be able to meet the full heating loads of the building without any auxiliary. Similarly, I can see sort of the same information plotted for the low stage. And the meaning of the balance point temperature in the low stage is a little bit different. So above that balance point temperature here, which is 27 degrees F, the heat pump is going to have more capacity than what's required by the building. And so what that means is that since our load is going to be lower than the low stage capacity or the minimum capacity of our heat pump is really going to start to cycle on and off above 27 degrees Fahrenheit. Now, in between that range of those two balance points, so between 4F and 27F, we're really going to be utilizing the variable capacity nature of our heat pump system. And so that's really where, when we're doing a variable capacity heat pump, that we really want to try to maximize the portion of time that we're operating within that range. In addition, I can also see that with heat pump number 1, and so with the selection that I've done, the high stage really very much surpasses the design objective that we had, which was to meet the building load at 17 degrees F. So I might have a question looking at this that, is there another option within the range that maybe that still meets my design criteria, but maybe sort of gets a little bit closer to that design target, and in doing so, perhaps start cycling at a little bit of a warmer temperature so that I do a little bit better job minimizing my on-off cycling. So I'm just going to scroll up here, and basically what I've done is under heat pump 3 and 4, I've plotted the high and the low stage for a 3-ton unit versus the 3.5-ton unit that I had been showing you previously. So now as I scroll down here, I can see that with my 3-ton unit, I'm really a lot closer to that air source heat pump target heating capacity. And I'm also going to have a balance point temperature for my low stage, which is a little bit milder. So that means that I'm going to be sort of minimizing the time that I'm going to be cycling on and off at milder conditions. And so this just, I think, as a designer, just provides us a little bit more information in order to compare some of the options that might be available to us. Now, as I move just to the right here, I'm going to have just another plot that is just going to show me, based on my balance point temperatures, how much of the total heating demand is going to occur above that balance point temperature. So basically, how much of the annual heating demands of the building am I going to be able to cover fully, sort of just using my heat pump system? And so when interpreting these graphs, the one thing that I recommend to you is that be sure that when you're interpreting them, that you use the heat pump number that corresponds to the high stage. So in my particular case, it would be heat pump number 1 or heat pump number 3. So you can see here for heat pump number 1, basically just about 93 or 94% of the total heating demand of the building is going to occur above that balance point temperature. In addition, in the tool, it's just going to provide you with a little bit of a table here, which really just summarizes the information that I already mentioned from the graphics. So things like the sizing option that you're looking at, your design loads, all the way down to your heat pump cutoff temperatures, how we're sort of responding to the design cooling, the thermal balance point temperature, and again, that fraction of heating above the thermal balance point temperature. So after I've sort of spent my time on step 5, comparing those different heat pump systems, the next step is going to move on to step number 6, which is really about delving into a specific heat pump more in detail and trying to identify the control strategy that we want to implement. So in this particular example, I'm going to say that heat pump number 3, which is sort of the 3-ton high-stage system, really got me pretty close to the design target that I wanted to use. So I'm going to select heat pump number 3 as the heat pump that I want to delve more into. And again, just to emphasize, if you are looking at variable capacity systems, please select the heat pump number that corresponds to the high stage system. Now, in addition, the tool is going to ask you, what sort of control strategy do we want to implement? And we might have a couple different options here. So we can run the air source heat pump all the way down to its cutoff temperature, which in this case, I think is around -22 that we entered. Or perhaps, we have a hybrid system and we want to understand what maybe is the best temperature to transition to a natural gas furnace, for example. So if I was looking at a case like that, I might select option B2, which is the economic cutoff temperature. So once I select that, I'm going to move down here and it's going to ask me just to provide a little bit of information on some of my backup heating system. So like what type of fuel am I using, whether that's natural gas all the way through to electricity, what's my natural gas rate if I'm using a natural gas system, and as well, what are my electricity rates? And we have the sort of flexibility to enter whether that's a single rate, whether that's a tiered structure, or a time of use rate all the way up to 5 different periods. And so when you enter that, and in the case where you have like a natural gas furnace, for example, what the tool will do is it'll essentially identify, based on the heat pump information that you've implemented, sort of what COP it becomes interesting to operate the heat pump versus the natural gas furnace. And then it'll delve into those heat pump curves and identify approximately what temperature that might occur. And so that can sort of help to identify what could potentially be a cost optimal transition between those two systems. And if I scroll down here, the tool will just provide a little bit of a visualization of that as well, plotting out the economic cutoff temperatures, and then just showing you here, based on the ratio of natural gas to electricity, what COPs would really make sense to run the heat pump versus the natural gas furnace. Now, in some cases, you might be really sizing the heat pump to really cover a large percentage of your heating load. and you're not really interested in putting in a natural gas furnace. We want to maybe put in sort of a supplementary electric duct heater to supplement heat pump operations on those coldest winter days. So in that case, what I would do is I would select electricity as my backup system, and I would then operate my heat pump down to its cutoff temperature, because essentially the heat pump should always be more efficient than the electric baseboards that you're operating. So there's really no benefit to transitioning only to the electric baseboards as long as the heat pump's going to be able to operate. In this particular case, though, I'm going to assume, let's say that we wanted to do a natural gas furnace, for example, with that economic cutoff temperature, just so that I can showcase some of the summary outputs a little bit later on. Next off is the sort of defining the backup system. So this is a tab that's really not a lot of user input here. The only thing that you're really going to be doing is indicating whether your heat pump's going to operate simultaneously with the backup. Because we have natural gas, it's not going to. And then it'll just provide a little bit of a summary of your backup size as well. Finally, we'll go to the checks and reminders page. So here, this will just provide you with some sort of additional things to think about during your installation. In this particular case, with the heat pump I selected, purposely I entered a really large maximum airflow capacity so that I could show you that the tool will compare the two values and then say, hey, maybe you should think about the capacity of the ductwork or examine that aspect a little bit more in detail. Last off, I'm just going to go quickly through the last two tabs. We have sort of a very basic calculation of things like GHG emissions, the heating costs, and the heating energy use as well. Just as a warning, these are done with the bin hour method right now. So if you are implementing something like a time of use rate, they're really not going to be fully captured within the current methodology. And again, if you are looking at a variable capacity system, the results that you're going to get with the heat pump numbers that are associated with the high stage are going to be more representative and more accurate. The last thing is you're just going to have a little bit of a summary sheet here, which just sort of, again, as the name would suggest, provides a summary of all the information and all the outputs that the tool has provided to date. You may be asking yourself, though, Justin, that's a really interesting example of a central system, but maybe I'm in a region where the homes are electrically heated. So, we're looking mostly at ductless systems, or, maybe the case that I'm looking at is I'm looking to put in that system in a current region that just doesn't have centrally, it doesn't have central ducting. So in that particular case, we're going to sort of talk a little bit about some of the multi-split systems as well. Now, one thing that I do want to emphasize is that the tool does a really good job of providing guidance on single split systems, but it's a little bit more limited in terms of sizing multi-split systems. So systems where you have multiple indoor heads. In those conditions, your sizing not only depends on sort of the overall load that you're imposing on the outdoor unit, but also the combination of your indoor units as well. So what we suggest right now is that if you are looking in a situation like that, the tool can really provide you with a lot of guidance on sort of sizing the outdoor unit, but we recommend that you confer with your sort of manufacturer supplier just to ensure that the selection of your indoor units is appropriate. Jeremy, as you mentioned a little bit earlier, has a great example in the addendum of a multi-split system as well that I think provides a lot of really interesting detail and flavor to this particular conversation. For today's example, though, I'm going to stick to something that's just a little bit simpler, and it's going to be a single sort of ductless integration of a system that's going to be serving the main floor. So imagine that we have a home, let's say in Montreal, and we have electric baseboard heating and we have no air conditioning. So we have a client that comes to us, they say, you know, I'm really interested in implementing space cooling, but I do want to cover a little bit of space heating as well. They want to focus sort of on the main floor. So primarily, let's say heating an open concept family room and kitchen, but perhaps, you know, that we're going to get a little bit of coverage to some of the additional spaces on that floor as well, just through some of the open corridors. From the load analysis, we know what our load is for that particular floor or space, both in heating and cooling. And as designers, we might have some more additional questions, like, you know, what's a good balance between heating and cooling? Again, how much of the load is that heat pump going to cover? And how should I set up my controls? And so that's what I'm really going to cover in the second example here, where we're going to focus on ductless systems. So here, on step one, instead of selecting centrally ducted, I'm going to go with just a ductless mini split single zone system. I'm going to select an add-on air source heat pump here because I'm going to be keeping those electric baseboards and I'm not going to be replacing one of the existing heating sources in the building. Now, when I go here, I'm going to be able to select what type of indoor unit I have, whether that's wall mounted all the way through to sort of something that might be concealed in the ceiling and sort of a horizontally ducted configuration. This particular sort of input is used primarily for tracking purposes, and there's not really a lot of dependency for the calculations on this step currently in the tool. So next, I'm going to move quickly to step number 3. Everything here is pretty much as is from the centrally ducted example. So I entered my location information for Montreal, and I'm assuming that, again, we've done a nice F28012 load analysis. So I've just entered sort of my heating and cooling loads. Next off, I'm going to move to sort of what my sizing approach is here. And again, here I mentioned that the client is, let's say they're primarily interested more in cooling-based sort of selections. So that's really going to say to me that I'm probably going to look at option A or option B. So both of these are really based on the cooling load that you're going to be entering. And so what happens is that when I select option A or option B, the tool is going to sort of identify a target cooling capacity range, which is between 80 and 125% of my design cooling load. And it's just going to populate that out for me here, and then as well plot it out as a little bracket in my graph. The only difference between option A and option B is that in option A, we recommend that you sort of fit your high stage to fall within that range, while with option B, it's more focused on trying to fit the low stage within that target cooling capacity range. For this one here, let's say that we're going to go with option B. We want to extract a little bit more heating out of our system in addition to supplying that cooling that our client was looking for. So as I move to step 5, again, the inputs are fairly straightforward. Entering the same sort of information here regarding my capacities, my efficiencies, and I've also added a little bit more information about the performance at the cutoff temperature, which in this case is around minus 13 degrees Celsius. And as I scroll down here, I can see that you know, I'm plotting out those heating capacities. And I can also see here when I'm looking at option A and option B, how my capacities respond in cooling as well. So what I can see here is that Heat pump number 1 is my high stage, heat pump number 2 is my low stage, and my low stage sort of falls within the bottom range of that target cooling capacity range, while my high stage sort of hits the, just sort of touches the maximum of that cooling capacity range, which is really a really ideal selection. Now, if I scroll up, I also plotted another unit because I just wanted to sort of emphasize one final thing. Some ductless systems have what we refer to as really high turn down ratios. So basically the percentage sort of reduction between maximum and minimum capacity is quite significant. In those cases, you want to be really careful because while your low stage might still fit within that target cooling capacity range, your high stage might really exceed the capacity range that you're looking for. And that's something that you really want to try to avoid if possible. So even when you're looking at option B, you want to try to have your high stage capacity as close as possible to the upper limit of that target cooling capacity range. The last thing that I want to emphasize on this particular example is just how you would set up your backup system. So basically here I have electric baseboards, so I select my backup heating system as electricity. And basically here I'd want to select option B1 for my control, which is operating my air source heat pump all the way down to its cutoff temperature. Everything else is pretty much quite similar in terms of the rest of the outputs and steps of the tool. In step 7, the only difference is because I now have an electric auxiliary system, I can have sort of a parallel operation of my heat pump and my baseboards as well.